All right, hello everyone. So our project is emotion recognition on a Raspberry Pi. Our group team was Evan Apinis, Sam David, and Matthew Lund. So for our project, we were aiming to do facial emotion recognition on the Raspberry Pi. So we wanted to design and develop a machine learning algorithm capable of identifying emotions. So it's going to process visual input data captured with a live camera, and the data is going to be processed on the Raspberry Pi uh, due to its embedded size and easy integration with the camera sensor, and it's going to predict the emotion being displayed. So to train the actual model, we use the FER 2013 dataset, facial emotion recognition 2013. It's commonly used in a lot of academic research papers. Um, it has some limitations, so namely, I'm going to show some of the images here. They're roughly all about 48 by 48 pixel grayscale images, so the detail shown is very low, and we've seen from papers that accuracy has been an issue. There's model overfitting, and to combat this, what we did was um, in our actual code implementation, we trained the model on several different architectures. So we had a ResNet 50, ResNet 26, MobileNet, and then this EffectNet HQ. Um, and we used this to find a good starting point. So we did a performance analysis across different model architectures to find the highest accuracy base point. And then from that, we can work on making sure that it's going to run in our embedded application. And so to actually run in our embedded application, what did we do? Well, we did a quantizing and pruning approach to the base model. So we took the most effective model from our main repo branch, which is this MobileNet v2 EffectNet HQ. Um, and model fits labels. So this pre-trained EffectNet HQ model has originally about 1,000 labels. Now, for the FER 2013 dataset, there are only 7 labels. We have happy, we have sad, neutral, fear, surprise, anger, disgust. So we fix the model to then only predict across these 7 labels. And then we implement pruning and quantizing to reduce the size of the trained model. So that way we can implement it on our Raspberry Pi. And as such, for implementing it on the Raspberry Pi, there was a couple steps. So we used a Raspberry Pi 5 and then an IMX 708 camera module. So this is just a Raspberry Pi camera module V2. It has a ribbon connector and it connects into the CAM1 port of the Raspberry Pi. Um, and then from that, we used a OpenCV Python library, and this is great for capturing video feed and then displaying it in a box, and I'm going to show a demo shortly. PyCamera 2, and then obviously our pre-trained torch model. All right, so to wrap up after the example, I'm just going to give a bit more background context on the model itself, and then some of the performance metrics between the quantized and normal model. So to start, I had said we'd use the MobileNet v2 model architecture. So we used MobileNet with EffectNet for the FER 2013 dataset. Here's the model architecture itself. Several layers of these bottlenecks, and then this is the actual figure for the bottleneck itself. So it's a fairly large, robust model, and yeah, it performed the best. And these were the performance analysis between models. So we can see this is the MobileNet with EffectNet with the lowest validation loss, highest accuracy, best precision. So this sort of motivated our choice for that. And as far as on-device measurements, starting with just the model size comparison, we have the full model, so not quantized, not pruned, and that was about 13.5 megabytes in size. And then we pruned and quantized the model 25%, and we got a final file size of 8.68 megabytes. So I have tested the models on the Raspberry Pi hardware, and I have 4 different comparison sets here. So the first is the idle configuration. So this is no model being run, just sitting on the desktop, sort of as like a baseline power consumption metric. So we see that it consumes about 2 watts at idle with very low CPU usage load. The next test was a no model but display window. So this is using the OpenCV Python. So it's capturing video from my feed and displaying it back, but without any inferencing from the model itself. And so we can see that already it's using 330 megabytes of memory, but still low CPU usage and a significant increase in power consumption. So I'm going to jump to now the bottom row. We have the full model. So this is display window plus inferencing, and we see that the total memory usage reserved is now 470 megabytes with 37% CPU usage and a bit over 5 watts for power consumption. As well as the inference time was about 130 milliseconds. So we're targeting somewhere close to about 10 frames per second. The power consumption metric is captured by sampling the PMIC, the power management IC of the Raspberry Pi, which will provide core voltages and core currents, and then we can compute the power and sum it up. It's sampled about every half second over a 10-second window to get the average power in that time. One thing to note about inference time is there's sort of a trade-off with inference time and frame time. So the higher the inference time, the smaller the frame time is going to report, which is why I didn't include it here. And that's just due to limitations on the frame rate of the camera itself. Like if we use the no model, the frame time would be around still 150, maybe 50 milliseconds. So it's not too important, but the thing I want to point out here is that for the quantized and pruned model, we've now decreased our memory usage from 470 megabytes to 430 megabytes reserved. Our CPU usage is down about 5%, and we can see sort of a similar reflection in the power consumption, where we're now below the 5 watts at 4.69 watts. So again, it's an increase over the just pure display window, but we achieve less than the full model, which is our target. And we also decreased the inference time by about 20 milliseconds, but this is where that trade-off of inference time and frame time comes in, because despite decreasing the inference time, the video feed achieves about the same frame rate because we've now increased our frame time. And that's just to say that a very long inference time gives the Raspberry Pi and gives the camera module a chance to fetch its next frame. So overall, we can see the effects of the quantization and pruning are successful.